Title. Well, thank you so much. Thank you all of you for being here. And of course, thank you to the Spectrum X team for inviting us, for having us all here. I'm going to spend some time I'm pretty excited to present to you some of the work that we've been doing for the last few years. Let's see. All right. I would like to start by talking about what we think are some of the key barriers in experimental wireless research, right? So you have access. One of them is access, which experimental wireless equipment is pretty expensive, right? You have high-end servers, channel emulators, software-defined radios that provide this flexibility that maybe, that allows you to innovate beyond what you can do with, let's say, some regular commercial off-the-shelf equipment. RF enclosures, chambers, you name it, right? Hey, even cables, right? You need high-grade cables and wires, and if you ever done any experimental wireless research, it's surprising the amount of wires that you need to do that, right? Lacking this infrastructure, this research infrastructure, impacts the training and education of the future researchers and engineers. So the other key barrier here is one of replication. Each lab, typically has its own mix and match of software and hardware environments. And that kind of leads to, unlike analytical research, it kind of leads to this amplification loss, right? Where you have limited replication and reproduction of your experiments. So the challenge here is one of empowering experiment-based wireless research at a scale and speed that is not possible today. And we offer one potential solution, which is, just being able to have shared, open, and configurable software-defined platforms and test beds, which leads me to Renew, okay? So Renew is a collaboration between several institutions, including Rice, Yale, University of Michigan, Texas Southern University, and we also have this partnership with the Powder Project, which is led by the University of Utah. So we're one of the NSF-funded platforms that conform maybe you've heard of it, the Platforms for Advanced Wireless Research, or POWER. And just in a few words, Renew consists of a massive MIMO research platform, and it features a hardware deployment that is located at the University of Utah campus. We have open source software, and we also have publicly available data sets, okay? So now you may be wondering, why massive MIMO, right? So the reason is that it's one of the key candidate technologies that has the potential for satisfying the performance needs of 5G systems and beyond, right? So that's one of the crucial things beyond for choosing this technology in particular. Now here's just the agenda for the rest of the talk. I'll give a brief introduction to massive MIMO. Very basic, and then we'll move on to describing Renew in more detail, and we'll talk about the deployment. So, hardware, the actual deployment at Powder, and some other deployment that we have at the university, at Rice. And then I'll move on to talk about some of the software data sets and some of the research that the platform and the different software tools have enabled. So, it's no surprise to any of us that the world is experiencing a fast growth in mobile data traffic, right? Most of us have seen plots like this, where you have, this is Ericsson's mobility report from June 2023, where it shows the mobile data traffic per smartphone and projected onto 2028, and for the different markets around the globe, right? And you can see, it's pretty clear. It's a tremendous, pretty fast growth of mobile data traffic. So the question that now the mobile carriers are kind of dealing with is, how do we cope with this growth? So now let's consider a cellular system where you're looking at the network throughput, so essentially the number of bits per second per square kilometer. This is effectively translates into essentially the spectral efficiency, the bits per second per hertz per cell, the density of your network, so the number of cells per square kilometer, and the amount of spectrum that is available, right? So if we are interested in increasing the network throughput in an effort to cope with this growth that we saw in the previous slide, so essentially we can increase at least one of these metrics, right? So let's say everyone wants more spectrum, but we all know that spectrum is pretty scarce, right? And especially at this sweet spot, the carriers tend to prefer because of their ideal signal propagation characteristics that provide this balance between coverage and capacity. There's also densification. So you have a higher intercells. You can keep adding small cells, some smaller base stations, but then you keep increasing your intercell interference, right? And it also can be more expensive. It's going to be more expensive. A third option is to increase the spectral efficiency, right? So we want to increase the number of bits per second per hertz per cell. And one way that we can do this is by adding more antennas to the cellular base station, right? Okay. So now we're going to explore, this is the option that we're actually going to explore throughout the rest of the talk. So let's consider this very basic scenario, right? Let's consider a single antenna base station where we have that is serving 3 different users, right? Single antenna base station, if it wants to serve these users, has to do it essentially one at a time, right? And it could do something very basic as just round robin, right? So just serve one user, serve the next on the next time slot, and the next on the next time slot. So you end up having essentially sending one data stream at a time, right? But we can do better. And let's see, now let's assume that we add a second antenna to the system, right? We can actually feed the same signal to both antennas and essentially the same phase and amplitude. And we're going to observe that in one direction, you're going to have this constructive interference, right? In this case, in the x-axis. Now, depending on the separation between the antennas, you can also experience some destructive interference and fully destructive, maybe, on a different axis, in this case, the y-axis. You can actually swap this behavior, and if you by modifying essentially the relative phase between these signals that you're feeding to the different antennas, you can have destructive interference where you used to have constructive interference, and the other way around. Okay. Now that's along the different axes, right? Very simple. What happens when you have another where your device is somewhere in between that? So essentially, what we're trying to guarantee is that there's going to be constructive interference at this location, right? And we can do something similar. Essentially, we can play with the relative phase that is being fed to the antennas and kind of achieve this behavior where the energy is directed in that particular location, right? So therefore, you can see that we can keep adding antennas. And we're actually, by having more antennas, what we're doing is creating beams, right? Essentially these pockets of energy that are going to be focused in a particular direction. And if we keep increasing the number of antennas, we can actually direct this more towards a particular location, right? So there's more directivity. So you can see that the beam becomes narrower and it's more focused. So essentially it's going to reach farther, let's say, right? Now, you may be wondering yourself, how did we even get from this discussion of having, spectral efficiency, and now we're talking about beamforming? Seems that it came out of nowhere, but the reason is that it turns out that we can leverage all the many antennas in an array to beam towards different users, okay? So this means that you can actually, you can send data to the different users at the same time using the same frequency and time resources, right? Essentially, you're serving all these guests at the same time. What you're doing is effectively increasing your spatial reuse. You have higher power efficiency, and you can reduce the intercell interference. And in general, the base station has, to be able to do these, to beamform to the different users, it has information about the channel to the different users. And it's able to compute a set of beam weights that then allows it to essentially do pre-coding and create these beams, okay? So, and in theory, you can actually serve as many users as the number of antennas, but of course, in practice, this is not the case, right? So, in other words, essentially what we're trying to do here is increase the spectral efficiency. So that's higher bits per second per hertz. And effectively, if we look back at this example, we have a single antenna that is serving one user at a time. Now we have this antenna array that allows you to serve the 3 different users at the same time, right? And yeah, you can continue the next flood, you can do it again and again and again, but now you're serving 3 guys instead of 1, right? So this is how you increase your spectral efficiency using let's say a mini antenna system like massive MIMO. So this was an extremely basic intro to massive MIMO, but if you want to learn more about it, just about the theory, how it works, of course, there's Professor Marceta's seminal paper from 2010 on cooperative cellular wireless with a limited number of base station antennas. There's this paper, the Arcos paper by one of our own, by Clay Shepard, and essentially where he built this prototype, and it was essentially the first reported massive MIMO base station architecture. That was back in Movicom 2012. And if you don't want to read any technical papers, there are some excellent online resources, videos, papers, blogs that I've seen by Professors Emil Bjornsson and Eric Larsson. Here's one link, for example. So yeah, those are all great resources to learn more about massive MIMO. All right, so now I'm going to move on to Renew. So I'm going to provide you an overview of essentially what we've been working on, what's available, and what you guys can do with it, right? If you're interested in doing any research with it or using any of these tools for whatever purpose. Now, Renew is part of the Platforms for Advanced Wireless Research Initiative. So this is also known as POWER. And these deployments are essentially the result of a $100 million public-private partnership that was funded by the National Science Foundation and an industry consortium that has many of the leading wireless companies and associations. So you can see these associations and companies here on the left. And the project is primarily managed by the Power Project Office, so the PPO, which is co-led by US Ignite and Northeastern University. So, we have these 4 different platforms located at different areas, and each of these has kind of a different focus. So the Cosmos platform in New York City has mostly a millimeter wave focus. You have ARA located in central Iowa for rural communities, AirPA in the Research Triangle, and this is more for aerial wireless experimentation. And of course, we have our own platform in Salt Lake City, the University of Utah campus, essentially, that consists of a diverse set of, SDR-based research that you can do there, and of course, massive MIMO. So, although Renew started with Power, Renew as we know it now, it has actually a longer history. So it started with the first generation of Argos. So this is the mini antenna platform that features several WAR boards, SDRs, and it was built in Rice back in 2011. This kind of evolved to Argos V2 that used a more, let's say, it was actually a newer generation of the WAR boards. It was a more compact form as well. And, these prototypes were built primarily by PhD student Clay Shepard, who, along with Ryan Guerra, another PhD, Rice former PhD student, they co-founded this company called Skylight Wireless. And then, they began building more modular and scalable massive MIMO systems, now with the goal of commercializing these, right? So that's kind of what led to Argos V3. And then now they kind of changed the name. It's now FARS V1 and V2. So FARS V2 is the newest, their newest system, essentially. So now, before Renew existed, our massive MIMO deployment at Rice was known as ArgosNet, okay? So we took these different components and we kind of deployed some of them across Rice campus. And, it's something that we use just for internal research, our own students and partners, right, from some of our partners outside of Rice. But once Power came in, essentially when Renew was born, Renew started leveraging the fundamental work that we had done in ArgosNet, right? So this allowed us to, add new functionalities to it. And now these functionalities were later incorporated into Power, right? So that is deployment located at the University of Utah. Now, Renew by itself consists of 3 key components. One is a public and private deployment. So essentially, you'll see the Powder deployment and also our let's call it our prototyping deployment that we have at Rise, right? That is mostly not for public use, just kind of for ourselves. So then we also have the open source software, and we have a bunch of data sets. So, during our experiments, whenever our students collect some data, we try to make all this publicly available, and we're kind of, as time progresses, we're kind of becoming better at, kind of putting all this together and documenting it. So the main goal is to have a pretty rich set of data sets that people can use. And interestingly, we've seen that a lot of research groups across the US are super interested in this, right? In many of them don't even try to use the platform, but they look at data sets and they see, okay, this is something that was already collected that I don't need to collect myself again, right? So they leverage that, and we've seen a bunch of publications using these data sets. So now, before I talk about the deployments, I just want to describe briefly some of the hardware that we're using so that you kind of know what we're dealing with, what's available out there, okay? And we're mostly working with FARS V1. So, just prototyping through SDR. These are SDR modules, and the building block of these massive MIMO systems are the Cyrus software-defined radios. These are 2x2 SDR transceivers. And essentially that means you have two TX chains, two RX chains, and it supports anything from 400 to 3800 megahertz frequencies. And the maximum bandwidth you can have is about 40 megahertz. Now you can see here in the picture, we have, it has an interchangeable front end. So this is just a dev front end, essentially allows you to do some development, especially for in-lab experiments and development. No, it doesn't have any amplification or attenuation, so it's just the dev board, right? But you can swap that for, let's say, a front end that works in BRS bands or CBRS bands, right? And those, of course, comes with all the different amplifying stages and some attenuation, etc. Now, we also have, the transceiver here is actually consists of a line microsystems chip. So this is an LMS 7002M, and it contains a Xilinx sync system on chip, has some off-chip memory, and you can actually use these devices by themselves. It comes with a barrel power connector and Ethernet, but you can also, you see this bus in between, this upstream and downstream interconnect that allows you to do this to daisy chain them, right? So you end up with something like this that allows you to form essentially a radio head, okay? So now you can have, you put some of these together, and in this case, you have, or we're showing here 4 irises. It really depends on the antenna spacing. So for BRS antennas, lower frequency, you have 4 irises. For CBRS antennas, which are smaller, you can put up to 8 irises together, right? These are dual polarization antennas with a gain of around 3 dBi. And you have about 12.8 gigabits per second data rate for each one of these radio heads. Now, then what you can do is you can actually, these are essentially like pizza boxes, right? They can stack on top of each other. So you form a base station by stacking these multiple radio heads. You can have kind of a maximum of 96 antennas. We typically have deployments of, between 32 and 64 antennas, right? That's typically what you'll find when, if you were to use one of our systems. And you can get actually, you can see here, there's a hub, right? There's a hub here that essentially, this is where all the different chains, radio heads connect to through fiber, right? And you can think of it as a master. And there's a backhaul through this hub that gives you 20 gigabits per second. So now let's move on to the powder deployment, right? So we have deployed, we have 3 base stations located on 3 different rooftops, okay? We have also deployed some UEs. We're actually in the process of deploying other UEs across, okay? So you can see here that there's a client pretty close to the base station. Actually, this setup is what we call kind of an high SNR setup. We have multiple clients in the base station all located on one rooftop, right? So that gives you a lot of flexibility on the power ranges that you can handle. But then you also have these other base stations that are pretty far from each other. there's actually, you can still establish a link between those two. They're about 600 meters apart, but you can still listen, they can still talk to each other. And like I said, we're going to be deploying more UEs pretty soon. And somewhere, these are kind of some of the potential areas that we're looking at. So we'll post more information once that's done. Now, so by the way, here you can see the website to Powder. I encourage you, if you're interested in knowing more about the platform, please go here. They have a ton of great information in there. You can see all the systems that are deployed, the different tools that you can use, all the different SDRs, not just the massive MIMO stuff, but you can do other very cool stuff in there. Again, essentially, you can go in today, you can create an account, and you can start using their system right away. Well, almost right away. Anyway, they have a pretty nice system for just reserving the different devices, frequencies that you want to use. And yeah, I mean, once you're in, you can actually, if you're interested in using the massive MIMO system, you can talk to us and we'll kind of guide you in how to proceed, right? How do you run your own experiments and how to use the software that I'm going to be describing now. So here's, I talked about this kind of a high SNR deployment in one of the rooftops. So, well, this is kind of rotated, but you can see the array and client location 1, 2, and 3. So it's actually client sites because you have a couple of UEs on each one, and each UE consists of 2 antennas, right? So where you see 2 of these circles, you actually end up having emulating, let's say you can have 4 UEs, right? Because you have 2 antennas for each one of them. Anyway, so you have the array, you have the different sites. We've deployed this first site, the second site. This one is still under development. Hopefully we'll have it up soon as well. Now that was for the Powder deployment. So we also have another deployment. It's essentially our RISE development test bed. And this is actually funded by different projects. So this is something that we've been building throughout the years, right? Even a lot of these started even before Renew. But this allows us to do a lot of the prototyping. So essentially, let's say we develop a new feature. Let's say some researcher is interested in a new feature for the massive MIMO platform, right? They talk to us. They said, okay, we're going to develop this for you guys. We do a lot of in-lab development. Then we kind of move it to our outdoor deployment and here at RISE, and we do a lot of testing. We make sure everything's working fine. And once that's done, then the next step is kind of to move it to the Powder deployment at Utah, right? And that's the one that you end up using for the most part. We have multiple projects funding this, and we use this for multiple projects, so including Renew, a dynamic spectrum sharing project as well, and Oscar, which is essentially playing with drones for having, kind of having autonomous, data-driven mobile sensing, right? And all the communication between the drones. So it's also a pretty cool project. We have some robots that you can move around, right, for mobility scenarios, and some CPEs, some fixed CPEs, and some mobile users. So now let me talk a little bit about the software that we have. Okay, so we have everything is available. Everything is open source. You can find it in our GitHub repositories. We have a wiki as well that explains all of this. We're continuously adding more stuff to the wiki and trying to explain better what we have. So if you're interested, please go in. If you have any questions, let us know. Now, the software our software kind of divides into 2 major, let's call them frameworks, right? One is Renew Lab. So Renew Lab actually consists of a combination of C++, Python, and MATLAB libraries that enable a pretty wide range of experiments, right? You can do real-time channel measurements, and then you can post-process all this data. So we have all this measurement framework is developed essentially in C++, and then we have a bunch of Python libraries that allow you to post-process that data. Then another aspect of Renew Lab is this tool is more of a prototyping suite. Essentially, it's like you have your MATLAB simulator, but with hardware and the wireless channel in the loop, right? So you do all your development in MATLAB, and then you take your IQ samples, you put them on your SDR, and you trigger transmission and reception, and essentially, everything over the air, but do all the processing and pre-processing on MATLAB. And the nice thing about this is that, of course, MATLAB is well known for having a pretty rich set of libraries that you can use, right? And also Python now. So just to give an example of how you run the sounder, right? So you have different UEs connected to a host machine and then the base station on the other end. So the first thing you do is you configure a schedule, right? Say, essentially that says who's going to transmit and when. Then the base station does some sort of beacon sweep. So you have a known signal that allows you to synchronize the different users. And I mean, you have an array, so might as well beam sweep it, right? You take advantage of that beamforming gain. And once the UEs essentially capture this beacon, they're waiting for this specific signal, right? They already know what their schedule is going to be, so they know when they're supposed to transmit. Essentially, that synchronizes them, and they can start sending pilots on the uplink. And of course, you can also, you're actually flexible enough that allows you to put some data in there, right? So if you also want to do some demultiplexing, some, let's say, receiver beamforming, you can have the multiple UEs transmitting the data simultaneously. And then during post-processing, you can analyze the different channel traces, and you can also analyze, try to do some demultiplexing and implement some of those MIMO schemes. So the sounder configuration is highly flexible, actually. It it kind of allows you to change many of the radio parameters, sample rate, frequency, TX and RS gains, the framing structure that I mentioned, frame length, symbol length, etc. And of course, it allows you to pick the different radios you're going to be using, right? And you do that by serial number. And there's also, you can send different waveforms. So far, we implement a few 5GNR and 802.11 waveforms. You can opt your own as well. You can essentially put that instead if you're interested. And I mentioned this schedule. This is because it's pretty important. So essentially, we divide transmissions in frames, and each frame consists of a different schedule, right? And you can see here, so different letters essentially means, hey, the B is a beacon. So during that time slot, the base station is going to transmit a beacon for synchronizing the users. Second and third time slot is pilots from the different users, right? And typically we do this time orthogonal so that they don't overlap. But later on, they can all transmit their data, uplink data at the same time, right? And since you know the channel that you estimated from these pilots, you can try to do some demultiplexing. And then you can also send some data on the downlink. Now, remember, you do all this transmissions pretty quick in real time and store all the data in an HDF5 format file. So this is a great format for this because it supports not only metadata, but also multi-dimensional data sets. So essentially we're recording, depending on what you send, we can record the pilot groups with all this, these different dimensions, uplink data and the downlink data, right? And this is what we use the most. And, once you collect this, you can post-process this using our Python tools, right? So you can do some data verification. What that means is, you can do everything from a pretty fast check, trying to look at, let's say, your pilot, look at the IQ samples and see what's going on there. You can look at a correlation across the different frames, but you can also do some other more, go a bit deeper into this deep inspect mode that allows you to check the validity of each one of the pilots, essentially. So for instance, you can see here this map here, right? That you can see, you kind of expect this dark color, blue color. If it's, if you see these gaps, these white gaps, you can tell that, okay, I've dropped some frames here. And then for some reason, this antenna is giving me a lower SNR. So you can do that sort of analysis. And like I said before, you can actually transmit concurrent data from the users. And what that allows you to do is later on, you can implement some schemes for the multiplexing, right? So either it's single user beamforming or multi-user beamforming. We already gave you some tools like for doing conjugate or seer forcing. You can implement the other schemes yourselves, of course. And another very interesting tool that we have is, this for your analysis, you can do this channel distribution fitting, right? So you can evaluate the channel gains across the different antennas and the different frames for each one of the users. And then, you can choose different distributions and kind of look at what minimizes some sort of error metric, right? you analyze the goodness of fit, and you know, it's a neat tool to have, at least so that you can have a kind of an idea of what your channel looks like, right? What's the distribution of your current channel? Now, I did mention this other prototyping suite. Everything I've mentioned so far is for the sounder, but we also have this other tool that allows you to generate signals in Python and MATLAB, and then you know, you load those Psyche samples on the SDR and just trigger transmission and reception. You know, in the sounder, essentially, you were transmitting a lot of data back to back, right? All those frames, one after the other. For this prototyping suite with MATLAB and Python, this is more of a one-shot thing. So it's pretty good for prototyping, and essentially you do, you know, just transmit you do a single transmission, and then you look at what you receive on the other end, right? So essentially, if you want to look at some different waveforms, that's one of the things that you can do. Different channel estimation schemes, you name it. So that's for ReneoLab. Now, there's another pretty powerful tool called Agora, or framework called Agora. This is a real-time massive MIMO physical layer processing for both uplink and downlink. So it's all software-based, multi-core implementation for both the base station and the users, right? And implements both data plane and control plane. Currently, it supports both simulation and over-the-air transmission. So what this means is that you can evaluate, test Agora by itself, you know, just the baseband, or add some sort of channel simulator to look at communication between a user and Agora. Or you can actually take it all the way to hardware and evaluate it on scalar forest. And now we're working on support for USRPs as well. So Agora essentially focuses on this part, right? The phi. So everything in layer one. Now this is the key design, the key software architecture here, or the key design in Agora is actually to use all available CPU cores for the earliest available frame, right? So they essentially want to minimize the processing time. So Agora essentially what it does is it borrows this Cube-based manager worker threading model from web server design. And this allows you to flexibly control the CPU resource allocation and baseband processing, okay? And it uses this manager worker model with having one manager thread and many worker threads. And essentially what you do is you communicate via message queues, I mean. So essentially the manager thread creates a task, communicates it through messages to the different worker threads. Once they complete the different tasks, they respond back with a message saying, hey, completed this. And you know, one of the things we see here as well is that some of the threads, some of the worker threads, all the worker threads can handle the different types of tasks except the network I/O, right? So that is specific to some dedicated threads. Now, Agora implements performance optimization for massive MIMO to lower the overhead of inter-core communication, code vectorization with CMD instructions, and also fast ways to use matrix libraries, which are very important, especially when you're trying to do all this, pre-coding, let's say zero forcing, right? If you want to learn more about the architecture, here's a paper that explains that introduces Agora, right? And it talks about all of that, and it does a pretty in-depth evaluation of the system. So here's a more detailed diagram showing Agora's data plane, okay? Essentially, you have this interface to the Mac and Phi. You have these different buffers, go through this whole chain of encoding, modulation, pre-coding, IFFT, and then go to the base station antennas. On the other end, on the reverse, take the data from the base station antennas to FFT. If it's a pilot, essentially you use it for doing channel estimation and beam weight calculation. These are linear pre-coding schemes that are implemented. You do the modulation and decoding. Now, the nice thing about one of the key features of this, because we're trying to enable research, is to give you guys the hooks for, probing essentially the data that you want to see throughout the chain of events here, right? So you can You can essentially write some of this data to a CSV or HDFI file, and then you can do some post-processing on that, right? So that's, we have these are some of the available hooks and some of the things that we are planning that we'd like to implement in the future. So now I did mention there is several modes of operation of Agora. So different simulation modes and different channel sims. You can hook essentially Agora to a channel simulator and to a user, or you can just evaluate Agora by itself. But you could also take it over the air, like I'm showing here. And these are the SDRs that are supported. So we have some results. These are some RISE Lab results that we have. These are all presented in this paper. So if you want to go into details, you can take a look at it. For instance, there's this evaluation looking at 64 antenna base station and 8 different UEs. These are 4 millisecond frames, 512 DMs of carriers, 64 QAM, and it operating at CBRS, right? So the idea here, one of the key goals in the implementation of Agora was to satisfy the stringent delay and data rate requirements in 5GNR. So here, what they're looking at is the block error rate, trying to make sure that it meets 5GNR with this number of antennas and 8 UEs. And turns out the evaluation shows about 16 bits per second per hertz in spectral efficiency. We have a whole bunch of demos. I'm not really going to go into them kind of long, but there's some visualization tools. These are, through the years we've been putting them together, different configurations. I believe these two were collected on powder. This was in the lab in Rice. Probably shouldn't show this one. Has some Disney picture in it, so I want to have it taken down. But there's some very cool. It shows you essentially how to run Agora and how to get all this different the different plots, all the different analysis tools out there. Right. Oops. Right. So now I want to move on. That was for all the Renew software. I want to move on to some examples of published data sets that we have. So one of the bigger data sets that we have is from the Argos Massive MIMO channel survey, was done quite some time ago. And this was using Argos V2 with 96 antennas. So it was done at Rice University indoors and outdoors with static and mobility using this track that you see in here. The data is for 2.4 gigahertz and 5 gigahertz, and like I said, it's a pretty rich data set. We also have another data set that essentially resulted in this paper, SOPNOL, so full duplex massive MIMO. And again, it was collected with Argos V2 in 3 different environments: anechoic, chamber, indoor and outdoor scenarios. Everything was done at NASA facilities. And it essentially used 80 antennas and 4 different users. Again, you're seeing most of these, we have them all on our website. You can access all those data sets. There's also a data set collected also at Rice with Argos V2, 64 antennas, looking at downlink and uplink at bands at 2.4 gigahertz with a 72 megahertz separation, 50 different locations on campus. And there's this other data set, a more recent one, that was actually collected by some students at the University of Utah. And this was collected on the Powder platform, essentially using when for some time the base station was deployed inside of anechoic chamber. Right now it's no longer there. Like I said, it's on the rooftop, but we got a pretty neat data set. Well, actually we got a couple of data sets inside the chamber. And as a matter of fact, these data sets specifically has already been used for some publications. So now I have a few minutes, so I just want to go really quick over some examples of the research that this project and some of the tools that we have that have enabled. There's, for instance, this FDD Massive MIMO paper, FIRE, which essentially looks at, when trying to do downlink Massive MIMO or MIMO in general, multi-user MIMO, let's say, you need channel state information at the base station, right? You want to be able to create essentially compute those beam weights and beamform to those guys. but the overhead, as you start increasing the number of antennas, becomes pretty big, right? So it's just a rapidly increasing overhead. And what this paper tries to do is to use machine learning to model the physical environment from uplink transmissions and kind of try to predict the downlink channel. One thing I should have mentioned is this is for FDD, right? So even if you wanted to do, let's say, if you wanted to do uplink, essentially get your feedback or just the channel state information from the uplink, since you're using FDD, different frequencies for the uplink and downlink, you cannot really do that, right? It's only feasible with a TDD system. So these guys focus on that on FDD. And they use an Argos data set for this. There's another paper that actually looked at distributed massive MIMO baseband processing. So this essentially is leveraging Agora to scale it up and kind of distribute computation across different servers, right? This allows you to accommodate more users because they know that as you keep increasing the number of users and antennas, you're going to need more computational resources, and also the front haul bandwidth requirements just keep increasing, right? So they essentially propose this Hydra scheme. Very interesting stuff. And the paper, I had mentioned this one. So based on the data collected on powder using the MIMO platform inside the anechoic chamber, they look at directional arrival estimation and massive MIMO, and they propose this novel single sample DOA estimation algorithm for doing fast and robust 3D localization. There's another paper that is essentially physics-inspired heuristics for soft MIMO detection and kind of addresses this trade-off between throughput and VAR performance and the computational complexity that comes with that. And for that, they ended up using this Argos data set using 96 base station antennas and 8 static users. And the last one is actually one from our own team, from some of our own students, our own group. And this is called LensFD. So essentially try to enable full duplex through massive MIMO. And what it does, it uses a low-cost lens array and in combination with transmit precoding to reshape the effective beam patterns of the antennas in a massive MIMO array. And this kind of allows you to reduce self-interference. So for this, they leverage the Renew platform, both hardware and software. So also pretty good stuff. All right, so I think I'm right on time. I want to thank you all. Thank you all for being here. There's, again, all these resources here. If you want to learn more about the project, we have our main website. We have a wiki with a whole bunch of information on the different resources. And of course, there's a Powder website as well. And, if you have any questions you want to ask here or questions that may come up to you later on, please feel free to send me an email. Here's my address. And yeah, thank you so much. And just want to open the, any questions that you might have now.
Thank you very much, Oscar. I used the chat window. We don't have to use the chat window. It looks like we could open the floor for questions for people to either raise their hands or, depending on how many there are. One of my questions, and you had addressed it partially, at least in your discussion, was you mentioned that there were bunches of data sets that were gathered, and you know how it is, the devil's in the details of of exactly what was captured, when it was captured, and this. Is there a way to physically to what level is the detail in terms of being able to understand the exact scenario under which the captures were done and what exactly was captured, and on top of that, what the plan is for either future data captures, or can these sorts of requests be made for future captures?
Yeah. So it really is tricky. It's difficult, to have a data set that is. There's always a lot of questions. Even for instance, this data set that one of the students at Utah collected, that now has been used by other teams for publications. It was a back and forth. It was difficult to make sure that we had a level of detail of what was done, right? It seems pretty pretty intuitive, but once you start, trying to characterize everything is not so much. So there has to be, we're working a lot on all those details on how the data was collected, pretty much try to document everything, right? For instance, on the other one, the Argos data set, we have pictures about where everything was taken. We just try to put all the information there. But there's this back and forth, right? That it helps us as well, kind of put better documentation out there. So yeah, it's been hard, but I think we're doing better.
I think Rick, you raised your hand and you said you have a question similar to Charles. So why don't you can either ask it directly.
Yeah. Can you hear me?
Yeah.
Okay. So my question is similar to Charlotte's. So how far are we along in this technology to have the carriers implement this in base stations? Is Qualcomm building things like this, and the guys that build towers and stuff like that? So where are we in terms of rolling this out? Because this could be a game changer if everything works out. Maybe the research isn't done yet, but how engaged are the carriers and their research and this kind of stuff? And when do you think we'll see this on a tower coming to your town soon?
Well, you can actually already find some massive MIMO deployments. So they've been working on it for some time. I remember the first base station I saw from Samsung was, I don't know, back 2013 maybe, or I don't recall exactly, but they're definitely out there, right? Ericsson has as well. I wouldn't be able to tell you details of how much, of course they're not going to make it publicly available, I guess, but of how many of those have deployed. Maybe we can find something, but I do know that they're out there, right? So,
Rick, was your question directed specifically to the Renew or Power platforms?
No, just the technology in general, because
Okay.
Renew, they would play into that, obviously, eventually, in terms of future exploitation. But does my iPhone talk to one today? That's what I'm kind of interested in, because I hear a lot about it. But when I look around, on infrastructure in my town, it's the same old, same old. I kind of know what they look like. And so is anybody going to be using this? And then I know, what's the relationship between what the carriers are doing and what you're doing, or do you know anything about that? Because it's been talked about a long time. Because you can really get spectrum efficiency up a lot with this stuff.
Right.
Yeah, and actually, this is Charlotte. Since I generated the first part while Rick had his hand raised, I was actually involved at Verizon Wireless in the early days of Power, and my question not only had to do with what Rick was asking, it's also how engaged are the wireless carriers when, in sort of in the research phase, because that was always an issue we had, is how to sort of have that cross-pollination take place earlier on. And I'm sort of curious, all the questions that Rick asked, but also just specifically the relationship that you have, at the research phase.
Right. We do talk to them. We've talked to Sprint. We talked to, I believe, Powder. Maybe they talked to Verizon. I don't know exactly. So for using, for instance, the Powder platform, I know for sure they've talked to the Powder team, right? So for instance, Kobus, who's the professor at the University of Utah, who's leading that effort. So yeah, we do get questions about what they can do and how. We've actually talked to more, I would say, smaller companies, probably more than the big ones, I would say. So there's been some interest from smaller companies about, kind of the stuff that we're doing and whether they've been able to use it or not. I feel like one of the things that maybe, what's hard to bridge that gap is that when they're using different hardware, right? If they want to implement something, they're limited to whatever their hardware, their system is, right? So I don't know. I mean, I think they could benefit a lot for sure. I know, for instance, that some of the companies are interested, are typically doing massive MIMO. They have this code book kind of beamforming, right? So we all know that just channel estimation and feedback, all that is tremendous overhead. So I think that's maybe one of the reasons why they do it. So I think there's a lot of research that can be done to continue to improve those things, and maybe that can be adopted later on by them.
Thanks.
Thank you.
Hey, Edmund.
Yeah. I have a question concerning the hardware.
Mm-hmm.
I've seen a Sync 7030, and you said that the speed between one of the radio heads of these bigger boxes is 20 gigabit, and you have the switch in between. So what is the link speed between the Sync 7030 and that local switch? Is that 1 gigabit or is that 10 gigabit?
Oh, it's a great question. I believe we had some issues with the client that kind of limited to 1 gigabit. We couldn't really quite reach the 1 gigabit per second for the clients. I know there was some other implementation. I wouldn't be able to tell you the details of that. That's more on the Scalar side for increasing that, at least for the base station itself. Mm-hmm. But we know that we can get to that, right?
Okay. So, and the other question is, so as I understand, your architecture is pure IQ streaming, where you have your timestamping of your IQ samples on the local radio heads, and all the processing is done on the central CPU, where you stream all the data in. So I've seen probably 4 or 5 radio heads. So you have, let's say, 2 10 gigabit by 5, so it's like in total 100 gigabit of speed you get into the server, and you do all the number crunching on the server. My question is, do you plan to do some processing on the FPGA? Do you use the Sync CPU in any way, or is that just not being used currently?
So for instance, the key, one of the things, initially we kind of try to do some stuff on the FPGA, but the goal became more of making everything software based, right? For flexibility, and that was kind of the goal of Agora, right? Trying to minimize what you were offloading to the FPGA. So try to do as much as possible on software. There's, that's why they do all this optimization using things like FlexRAN, for instance, right? Yes, for right now, it's mostly just for packaging essentially the samples and sending them back to the host machine. Mm-hmm. Yeah, for sure. And I mean, the couple of ARM cores in there are used more for just configuring things, just for control, not so much for the data plane. So the data plane is essentially goes essentially your RF and then through the FPGA and then back all the way down to your to your host machine.
Yeah, because I did SDR in the past, but now I'm mainly doing FPGA tools. And obviously writing Verilog is not the right thing for signal processing people to do. Yeah. So we try to make it as easy as possible. And there are tools where you can do Simulink and then generate bitstream out of your Simulink simulation. And we try to do that all in open source, like where you can write your DSP or signal processing in C and then generate the bitstream out of that. So because massive MIMO beamforming really asks for being on the radio head and not being in the CPU, because it's all about streaming data, and the CPU is not an architecture for streaming data. It's the FPGA is the thing. It's just that's so hard to program. So I hear that you mainly do C, your algorithms.
Yeah, mostly C++ for at least for Agora and the Sounder. Yeah, and like I said, some we leverage this SIMD instructions as well, right, for being able to deal with all this data in parallel, and so there's a ton of optimization because exactly what you're saying, right? So it's
I seen a lot of scheduling pain in your slides.
Yeah.
So
sorry, go ahead.
So I guess if we would have a tool which compiles your C code down to a bitstream in a massive pipeline parallel form, that would be something you would be willing to look into.
Oh yeah, Yeah. No, we're always looking at different ways of, essentially, let's just say that we haven't had, I guess, the scenario where we actually need to forcibly do it on the FPGA, right? So we've been able to get away with doing mostly on a host machine, right? Essentially on a CPU. So yeah, no, that's for sure. Well, and also, I mean, one thing we've noticed is, I mean, yeah, researchers, you can provide them very powerful tools, but if it's very difficult to modify things, they're just going to shy away from it, right?
Yeah.
So that's one concern always. So
yeah.
Even we were focusing 100% on the Sounder and Agora for some time, and then we started to get a lot of attention, different users, but they were all like, no, we want better Python and MATLAB tools. So then we kind of had to take some resources out of that and put them into MATLAB and Python, right? So yeah, that's a common theme that we see.
Yeah, because I like your architecture with the cross FPGA links on the radio head. That could be used, but I would take a bet that we don't use them currently, beside synchronization.
Yeah.
Okay, thank you.
Thank you.
Well, folks, we're actually at the top of the hour. I was going to ask another question on Open RAN and how much interaction either Renew or Powder Power were interacting, if any of these architectures were informed by that. But I think we better save that for an email thread. Is there any last minute quick questions before we thank our speaker? All right, thank you. I don't know, a little clap.
Thank you so much. Yeah, great meeting you, and thank you. Thanks for this. It's great.
Excellent talk. Thanks.
Thank you. Bye.
Thanks.